بسم الله الرحمن الرحيم. السلام عليكم ورحمة الله وبركاته. Entitled High Performance of Commercial Solar Cells Stacked by Crystalline PN Silicon Nanowires. This paper is to be published under the names of Lotfia, Nadi, Muhammad Izzat, and Yahya Ismail. Lotfia Nadi works at the Faculty of Science, Physics Department in the Laser Lab, and also at the International Center of Scientific Studies for ultra-fast lasers at the Niles at Cairo University. Professor Yahya Ismail works at the Center of Nanoelectronics and Devices at Zuwel City for Science and Technology, and Muhammad Izzat works at the Laser Center at Bani Suef University in Bani Suef. I think that it would be very interesting if I can give you an idea about my group and about when did I start to do nanotechnology. I really did start that in 2006 by preparing gallium nitride nanostructures by laser ablation of gallium metal, just without any liquid or anything. In 2006, we also grew structure of metal oxides by laser ablation and silica-assisted thermal evaporation. As a published work, formation of nanowires by laser ablation of graphite was in 2006 as well. 2008, we started to make structural and optical properties of the gallium oxide nanodots grown by silicon oxide assisted evaporation. In 2011, we did work on optical properties of gallium oxide nanostructures. And in 2011, we did work on gallium nitride nanostructures by laser ablation of metallic gallium. Then we really introduced the new work on liquid phase pulsed laser ablation work. We started this work in 2010 by preparing rare earth doped and undoped gallium nitride nanocrystallites through liquid phase pulsed laser ablation. And we did other work at Georgia Tech Institute together with Professor Mustafa El Sayed and Samah. And that was on energy transfer efficiency in europium doped zinc oxide thin films. And this has been published at the Applied Materials and Interfaces, which is published by the American Chemical Society. Then we started to do work on silicon nanocrystallites. We were so interested in silicon being as you know, most important in solar cells. Silicon nanocrystallites prepared by nanosecond laser ablation of silicon wafers in water. That was started in 2013, was finished then. And we did some other published work, structural and optical properties of nanosilicon fabricated by liquid phase pulsed laser ablation method in 2014. In 2014 also we did some work for the titanium oxide nanoparticles applied to antimicrobial self-cleaning surfaces. And we did prepare nanosilver by liquid pulsed laser ablation applied to textile industry in 2014. In 2015, we did some research work on photoluminescence properties of undoped and doped thin films grown by radiofrequency sputtering on sapphire substrates applied to surface science. Then we turned to be more interested on PN silicon nanowires conversion efficiency, which has been read at the Dubai conference in 2018. Now we will start with the paper for this conference. The abstract is simply written here. Since more than 20 years, silicon solar cells is dominating the world market. But the power conversion, in spite of world active efforts, is still around 23 to 25%. And this is the efficiency. Some people claim that they have gone beyond that, but this is the silicon solar cells that is on the world market nowadays. Our group, in an attempt to improve the efficiency, decided to fabricate a device by simply stacking crystalline PN silicon nanowires on top of a conventional silicon solar cell. Because of course, we thought that such a very widely used silicon solar cell industry now is not just going to replenish that and replace it by another material. So we decided that we would keep the same solar cells, the conventional solar cells on the market as it is, but try to add to it something else that would increase its efficiency. By forming nanowires, we prepared these nanowires applying the liquid phase pulsed laser ablation method. And these samples of the PN silicon wafers immersed in double distilled water were subjected to different number of nanosecond UV laser pulses from nitrogen laser of time duration 15 nanoseconds, having energy of 375 millijoule per pulse. The wires were characterized using high resolution electron microscope and Joule 2100 transmission electron microscope, and whether it's crystalline or not, we really use the electron diffraction method. The optical properties of the different prepared samples were measured, showing higher spectral absorption for the nanowires prepared by 400 laser pulses, forming sizes of mean length between 15.13 to 15 plus or minus 0.15 nanometer, and mean width of 1.64 plus or minus 0.15 nanometer of nanowire density 10 to 13 per centimeter square. They also showed relative blue shift peaking at 410.5 plus or minus 30.6 nanometer. The photoluminescence spectra provided the highest photoluminescence peak at 657.15 plus or minus 2.2 nanometer for photo excitation at 491.3 plus or minus 0.15 nanometer from the argon laser. Such optical properties suggested suitable optical properties of the nanowires to absorb solar spectra that is not utilized by the conventional solar cell and provide suitable and higher efficiency photons to be absorbed by the conventional solar cell, in addition to the transmitted solar spectrum. So in this case, we are amplifying the use of the spectral range, and the performance of the stacked device was determined by comparing the IV characteristics of the combined solar cell with and without the stacked p-n silicon crystalline structures, nanostructures. And we found that the efficiencies varied between 4 and 18.8% were detected, and the efficiency is for the p-n silicon nanowires prepared by 400 laser pulses. As an introduction to the work, we are going to give you an idea about what is really happening since the history of silicon solar cells was known. The evolution of crystalline and multicrystalline silicon solar cell efficiency is an old field of physics and industry. And this curve shows crystalline p-n silicon solar cells since 1940, where it was very low efficiency. And then in 1980, it started to increase to be, the crystalline to be in the order of 18%. And then it overcome that, and in year 2015, it raised to 25%, as reported in literature. The multicrystalline p-n silicon is the lower curve, and as you see, the multicrystalline is having less efficiency than the crystalline p-n silicon. This up till 2015. Now we can describe in a very confined manner the description of the commercial solar cells available in a work that has been published in 2009. So as you see, the efficiency curve, the corrected efficiency percent, started in the year 75, was approximately 9%, and in the year 2004, it went up to 20.4%. And the cell description is the last column, in which we have the industrial production companies, where SolarX and Georgia Tech produced most of them. As you see, the reported efficiency was raised from the year 1975, 10%, to 20.3% in the year 2004, and to 25% nowadays. Now, there are three types of solar cells that is being introduced into industry. The first one that started as crystalline silicon cells was really starting from the for efficiencies did not exceed 20%. Then the price per watt was around $50 per watt. As you see on the lower part, the green crystalline silicon cells is illustrated. Then came the semiconductor thin film technologies that started, of course, to exceed all other types using thin film technologies, silicon, MC silicon, that is the CIGS, copper indium selenide cells with yellow color that became cheaper as well. And then new generation concepts, third generation cells in the red color, as you see, is now predominating most of the solar cells on the market. And it costs between $0.2 per watt to $0.1 per watt, while when it started it was $3.5 per watt. So it is becoming cheaper. Another type which is now prevailing is the radial junction silicon nanowire technology. Here they use the nanowires technology in a radial junction silicon nanowire, as clear from the figure. This is low cost, and the substrates are low cost and conformable substrates, makes it more prevailing in the market. But still, it is not exceeding 25% efficiency conversion. So high efficiency of 15% enhanced the optical absorption of silicon nanowire arrays, and then effective extraction of photo-generated charges in the radial junction configuration. Low cost one, low silicon material usage, and the substrates are metal substrates. Lee et al. In 2010 and 12 estimated the advantage of silicon nanowires, and they pointed that there would be an enhanced optical absorption for the silicon nanowires. So the light would pass, the solar light would pass through the incident light, like through the rods, like on the right-hand side of the figure. And the curve for silicon nanowire array periodicity as a function of ultimate efficiency is seen on the right side, with an increase up to 24%. And in this case, the silicon film was 5,000 nanometer. The silicon array was clearly given in the black points. The efficiency is given in the black points. And it shows how the silicon nanowire array periodicity at the bottom varies from 200 nanometers to 1,400 nanometers. So we can conclude from this that silicon nanowire arrays with optimized periodicity offer an enhancement of absorption compared to silicon thin films with the same thickness. Silicon nanowire arrays would allow to reach higher ultimate values, reducing silicon material uses. So putting that in mind, we started to think about our work. We started to think about preparing silicon nanowires. The experimental setup used is a nitrogen laser, as seen on the right-hand side. The nitrogen laser produces UV laser light. And then we put the samples of the PN silicon into water, distilled water, and focus this laser light, the X-ray laser light from the nitrogen laser, onto the PN silicon sheets in a quartz cell in water, immersed in water. This experimental shows the high-powered UV laser in our laboratory. And this is Muhammad Izzat and Muhammad Fikri, students. Now Muhammad Fikri is a staff member, and this is the nitrogen laser is extended, as you see, and the laser beam is focused onto the laser cell, including the silicon PN sheets. After that, the samples of the silicon PN sheets taken from after bombardment with the UV laser. So the UV laser is the laser pulse, the pulsed laser, and the LP, that is the liquid phase, is distilled water in this case. Then we checked the photoluminescence of the silicon PN crystals formed into the water by a conventional photoluminescence system, where we can determine the spectrum of the silicon nanocrystals, and also we can take samples to identify by the high resolution electron microscope for the number and the shape of the particles, and also for determining the specifications of the rods formed, whether they are formed or not. So this is the results of our results. I will show only 3 types which has been recorded according to the PN silicon nanowires, high resolution transmission electron microscopy, to count the number of particles formed, and the electron diffraction electron microscopy to determine whether they are crystalline or not. And we used, of course, the UV laser, nitrogen laser, with the wavelength 337 nanometer to ablate the silicon PN sheets. So for these conditions, we found that the distribution of the size of the rods varies from mean diameter varies from 0.85 to 1.2 nanometer, with peaking at the value of 1.04 nanometer. That's mean diameter form for number of particles, number of particles against the mean diameter. As you see, it is peaking at 1.04 nanometer. This is the electron diffraction spectrum, which confirms the crystalline structure formed. And this is the high resolution electron microscope to see to count the number formed and per centimeter square. As you see, we have the scale into 20 nanometer size, and as you see, they are so parallel to each other. On the right hand side figure. And the results of this indicates that we, with the laser, UV laser 337 nanometer, the energy of per pulse from the laser to ablate the PN silicon sheet was 375 millijoule, and the pulse duration was 15 nanoseconds. Nanowire density was found to be 5 times 10 to 12 wires per centimeter square, and we get the mean length to be of 56.22 nanometer with diameter 0.3 nanometer. This is the other case where we utilized higher number of shots, 400 shots. The particles increased, the size, the mean diameter of the particles increased, and the mean number of particles also increased. And the crystallinity was also existing using the electron diffraction method, and the shape of the parallel wires are so clear on the right hand side with 20 nanometer diameter. So this is the outcome of using these conditions, that we can get nanowire density of 10 to 13 per centimeter square, that is increased than the first one, and the mean diameter was 1.65, and the mean length was 15.13 nanometer. This, as we increased the number of shots of the laser, we increased also the number of PN silicon wires produced, with the increase of the diameter to reach 5.76 nanometer. And the number of particles, as you see, increased to due to the increase of the power density of the laser. And it peaks at 5.76 nanometer. This gives the mean diameter. So, but it was found to be not parallel, and the rods formed were haphazardly distributed in the sample, but it kept the electron diffraction shows that it kept the crystalline structure. So in this case, we have we did produce for irradiation of 15 nanoseconds, we produced nanowire density of 5 10 to 10, and the mean diameter was 5.76 nanometer, and the mean length was 140.83 nanometers. Then we made optical absorption to see whether the range of solar spectrum will affect the absorption and will be absorbed into these different samples. And we found that as the sample size increased, then from 50 to 400, we found that the optical absorption increased from 0.56 on the average in the range from 400 to 800, and it increased up to from 0.8 to 0.8, from 0.56 to 0.8, that is increased in all the region. So this is the optical properties normalized absorption spectra for the PN silicon nanowire samples prepared. So the photoluminescence of the samples at 657.15 plus or minus 2.2 nanometer when excited by argon laser line of lambda 438 was found to photoluminesce on absorption of a wavelength 657, that is at the range where the conventional solar cells are actually not responding. So if we utilize this photoluminescence of the samples we prepared to be added up to the conventional solar cells, then of course this means that we are adding extra amplification of the solar energy arriving to the conventional solar cell. So we also measured the IV curves after treating the samples by ultrasonic shakers. Equal number of drops were placed on a glass slide by the fine needle and then covered by a thin microscope plate, and we get the IV characteristics of the conventional solar cell were measured with and without adding the samples the nano samples we prepared previously. This shows the very simple IV circuit and shows also how we prepared the PN nanowire samples where we used drops of the prepared nano PN silicon between a plate and a cover of a microscope. And we, on the right hand side, as you see, we have the conventional solar cell. And we have measured the IV characteristic without introducing the PN silicon wires and by introducing the PN silicon wires. And we excited the silicon, the PN silicon system. This is a conventional solar cell. And this is on the right side, the PN silicon nanowires prepared by the previous methods. And we used a solar simulator. We measured the IV characteristics of the conventional solar cell with and without the PN silicon nanowires. And we found that the efficiency increased all the time with all the samples. But of course, we see that with the samples that has been prepared at 18.8%, the the efficiency increased to 24%. That's to say, it became 24% than 25, so that we reach a 30% increase of efficiency. We can say the results achieved indicate that the PN silicon nanowires obtained by the liquid phase pulsed laser ablation of PN silicon wafers in double distilled water by UV laser showed increased cell efficiency, varying from 4% to 18.8% by stacking the silicon nanowires above the conventional solar cell, as illustrated in slide 25. The highest efficiency was obtained for PN silicon nanowires ablated at 400 laser pulses, distinguished by nearly parallel geometry as well as small spread in dimensions of the highest nanowire crystal density. Added to its optical properties that indicated highest optical absorption for photons in the range of the solar spectrum, high photoluminescence peaking in the spectral range of the conventional silicon solar cells, and this would be our successful utilization of the conventional cells that is existing on the market nowadays, with adding the new nano structures we prepared by the liquid phase laser ablation technique. Of course, all of these works were motivated by Professor Mustafa Al-Sayed, who is, of course, our motivating, we can say motivating agent in all our work, and he is always keeping in touch with all Egyptians in several fields. My research group is formed of Muhammad Azzat. He is a MSc student. He's now in Korea working for his PhD. And Mr. Ibrahim Marzu from the industry of solar cells company made by the Egyptian Ministry of the Egyptian Ministry وزارة الشؤون الحربية, ودكتور يحيى إسماعيل from the University of Zuwel, Habib from Niles, Abdel Qadir from Niles, and my colleagues, Professor Magdi Omar, Professor Galila Abdel Latif, and Professor Hussein Abdel Menam are supervisors with me in most of the research we are carrying out. I really do thank you for your patience, and if you have any questions, I would be very happy to answer it.